coulomb. So what you've missed is we started out with just a parallel plate capacitor with nothing in between it. That's what, and I gave, what's in blue here were the original dimensions. And we solved for these quantities. And now I separated the plates and put a dielectric in between, and so now we're just calculating what's happened, how it's changed. All right, so the electric field from the plates. And these are the equations that we basically have for this type problem.
We'd use the Q over A E naught, right?
Yep. And so I got the new Q, A is the same, epsilon sub naught is the same, so in essence, 1600?
Yeah.
And now the total electric field.
Uh, 800 newtons per coulomb.
What'd you get?
800 newtons per coulomb.
And how'd you get that?
You're switching out epsilon naught for epsilon, which in this case is just epsilon naught times 2, so it's just half what it was.
All right. In essence, I mean, thinking through it, but in essence, using that formula right here.
Yeah.
Recognize also, we should be able to get it a slightly different way. The fact that my voltage, ignoring the sign, the magnitude of my voltage, is just, should be the electric field times delta x, electric field strength times delta x. So it should be 12 divided by 0.015. Which I'm hoping is 800. Okay. Questions there before I change, before I change it? Now, recognize that, yeah, I mean, we're just playing around with a very simple capacitor here. All of it is about trying to control the current flow. So, as you, especially for the electrical engineers, as you get farther into it, you get more and more sophisticated ways of dealing with current flow, but we're gonna stick with just capacitors, resistors, and inductors in this course, and then you'll get into diodes, etc. And then there's some funky ones that I've read about but never seen that you could also get into. Felt loose. All right, so changing it around. Now I'm going to disconnect the battery. Let's talk about disconnecting the battery with this group. All right. If I try to do this, I get a capacitor all charged up and then I disconnect the battery. What's going to happen realistically is that as I take the lead off of the battery, there's going to be a small gap there. And if the capacitor is fully charged, and a large enough capacitor, basically there's going to be a spark, and this is going to discharge. To be able to disconnect a battery in real life, you need to be able to disconnect it on the order of a microsecond or faster. I cannot do that. For these type problems, I might throw the word ideally in there, but it's sort of assumed that it is an ideal disconnect so that I'm breaking the connection so fast I'm not changing the charge of the capacitor. So when the battery's connected, my voltage stays constant. When I disconnect the battery, now my charge is going to stay constant. But let's just start out with, all I've done is disconnect the battery. What changes or what stays the same?
You just said your charge stays constant?
Yes.
Q.
All right, so disconnecting here. So we now disconnect battery. So Q 1.42 times 10 to the negative 6 coulombs. Anything else gonna stay the same?
Would the capacitance stay the same?
Why?
Because, using the bottom formula over there, K epsilon naught A over D, none of those values changed.
Right, all right, so my capacitance is the same.
Your voltage would be 0, right?
Nope. There's still a potential difference. I still have a bunch of the positive charges and negative charges, so there's a potential difference between the two.
So when you look at it, you just look at the plates really for the change in voltage.
Right.
I guess when you disconnect the battery.
Yeah, I mean, before we were looking at just the plates also with the battery connected. It's just that I gain 12 volts here. Whenever I do a complete loop and end up back where I started, my potential doesn't change. At any one spot, to no matter what path I take to the exact same spot, there's no potential difference. So if I start here and go all the way around, I better have a total potential difference of 0. Well, I gain 12 there, which means I have to lose 12 there. So when it was hooked to the battery, yes, this fixed the voltage here, but really when I'm talking about voltage, I'm talking about the voltage between the plates at that point also.
So does that delta V stay the same since?
Why?
Well, looking at that top formula, if your capacitance and your charge has stayed the same, then your delta V would stay the same also.
Yeah, still 12 volts, that hasn't changed. And then my electric fields,
Doesn't area stay the same?
yep, areas, you said, don't they stay the same, or does the area stay the same?
Well, since area stays the same and Q stays the same, and the difference between the two plates is the same, then they would also be the same.
You sweeping statement for both of them, or just one of them?
I'm saying for both of them.
Okay. Yeah, because also the other relationship for the total, this E right here, I didn't write it, I thought it intensely, this is the total electric field here. Yeah, my voltage stayed the same, the distance between the plates stayed the same, so my total electric field also stays the same. So just disconnecting our battery, because we did it in such a beautiful way that we didn't discharge anything, nothing's changed in terms of our 5 quantities here. Now if we adjust it though, things will change. So what I'm gonna do is,
Would that also all stay the same if there wasn't a dielectric in there?
oh, you mean, had I gone from here to disconnecting?
Yeah.
Yeah, then it all would have stayed the same as long as they don't do anything else.
Okay,
But now if I do something else, if I disconnect and then do something else, yes, some things will change.
gotcha.
So, let's remove the battery. Or sorry, not the battery, let's remove the dielectric. We'll still keep it 1.5 centimeters apart. So now we will remove dielectric. And yeah, just do that. All right, so what happens?
Voltage is the same.
Why?
Because nothing happens to it.
We're not connected to the battery anymore, so.
Oh,
Yeah, this is in addition to what's already happened before.
okay.
Yeah, when I do a problem like this with multiple parts, where I'm doing various things to the parallel plate capacitor, it's always, I've done this, now this has changed, then I do something else, still with this change in play and so forth. I have had students in the past interpret it of, they're always jumping back to the original situation and then looking at just one change at a time. All right, so what definitely is gonna have to stay the same?
The charge on the plates.
Yeah, so that's still gotta be 1.42 times 10 to the negative 6 coulombs. Has my capacitance changed?
Yeah, it should be half of what it was.
Yep. So 5.9 times 10 to the negative 8 farads. So my voltage will change in this particular case.
Yeah. Wouldn't it be 24?
Let's see, it's, the voltage is Q divided by C. C got cut in half. So, yeah, 24 volts. Which is an indication of how much harder it would be to move a charge from basically one spot to the other. Yeah, so if you're taking a, I don't want to word this. So if I have an electron, yeah, if I was taking an electron from the positive plate to the negative plate, it would be more difficult because the electric field I'm fighting against is stronger. All right, what about my two electric fields here? The one from just the plates themselves and then the total?
The plates should stay the same.
Because the charge stays the same, so that's still 1600. And the total?
1600.
There's more than one way of getting there. Which way did you get there?
The dielectric was 2, now it's 1. Or, sorry,
So basically this one?
yeah.
Yep. All right. If you've also done this, so we've doubled the voltage, the distance stayed the same, so electric field would have to double. All right, questions before I change the problem? I've also done a variation of this problem where I said, just let the initial values be sub-zero. So this is C sub-zero, Q sub-zero, delta V sub-zero, E sub-zero, E sub-zero. And then express all the rest of them in terms of those initial values. Hopefully figured that'd just be a lot easier on students instead of having to do a lot of calculator exercise. But half the students still did the numbers. All right, so let's change it around a little bit. Why don't we start with what we started with before? We got a 12-volt battery connected to it. I got 1 centimeter difference between it. I got nothing in between, no dielectric. So we've got our original numbers. double the charge and cut the voltage in half. So, if I'm doubling the charge and cutting the voltage in half, what can I do?
Multiply the capacitance by 4.
And how would you do that?
What do you mean by how?
Yeah, I'm looking for specifically of what physically. All right, so
Okay.
let's throw in one other thing. The things that you can manipulate in order to achieve this are you can connect/disconnect battery. You can change and also change, we'll say area of plates, the dielectric, distance between plates. And what else do we have to manipulate? So this dielectric area, distance. Yeah, that's pretty much it. So those are the 4 things that you can manipulate.
The voltage would be half, cause it's cut in half. Right, and then the Q.
Yeah, how are you gonna cut the voltage in half?
Cause you wrote it up there.
No, that's what you're attempting. What I want is you to manipulate this capacitor, given those things that you could change, one or some. And in the end, I want the charge doubled and I want the voltage cut in half. What can you do to make sure that I double the charge on the plates with the voltage cut in half?
Capacitance.
Is that delta X the same as D?
Yes.
Okay. So if you make that distance half its size.
So cut the distance in half.
Yeah.
That's right. All right, so let's see what that changes. We cut the distance in half, then my capacitance will double, so that is 2 times the initial. And this is D equals 1/2 my original. My voltage stays the same, so this is still delta V sub naught. My charge would double. If I double the charge, then I double the electric field between the plates, so this is 2 E sub naught. And since there's still no dielectric, this would just be 2 E sub naught. So we've doubled the charge, but we have not cut the voltage in half.
At this point, if we disconnected the battery and moved them, again, half the distance to each other?
All right, so going to disconnect and make D equal to 1/4 D sub naught.
Yeah.
All right, so you disconnect, so now this will stay twice the original, so that's still good. My capacitance will be 4 times the original. And my voltage would now be, well, C times, let's see, voltage is Q divided by C. So Q divided by C, this would be going 1/2 the original. All right,
I guess move it to its original position then, instead of moving them closer.
wait, sorry, what?
I was saying, instead of moving them again closer, move them to their original spots, that way keep the charge, but the voltage would go the other way.
No, we actually did it.
Oh, okay, sorry, I had written down the wrong thing.
Did I get something backwards there? So.
No, I wrote down double the charge and the voltage.
Oh, no, okay. So another type problem, this is test 1B, or the second test material. And then I've done other variations of this, double the charge, cut the voltage in half to keep the electric field constant, type thing. And then a couple years ago, I did one of those where it was actually an impossible situation. So now I've added in if it can't be done, please show why it can't be done. All right, questions there before we actually get closer to the question that Joe asked at the very beginning. All right. Get back to parallel plate capacitor. So I have the two parallel plates hooked to a battery or some power supply. It charges up. If instead of it connected like this, suppose I change the connection to this. So I basically split the wire right before it gets to the plate and connect it to the plate in two different ways, two different places. Is that going to change anything?
Are they evenly spaced apart from the center?
Sure.
No.
If they were not evenly spaced, what would that change?
It would be like, so let's say you split it, if they were evenly split, it would be evenly distributed, and if one was closer to the other one, like on one side of the plate, so if one was towards the bottom more, that charge would be more concentrated towards the bottom.
It's still a conducting plate. The electrons are still trying to get away from each other.